2018 statistics. The last part is financial maths, so it's not worth a full 60. So we now have a mean in this question, a standard deviation, and a sample of 10 bars. And we're asked the probability between these two values. So anytime we get these stats questions, we do a sketch just to see where we're at. My normal distribution curve with my mean in the middle of 4.64. We're asked to test two values. One is greater than it, 4.7, and one is lower at 4.6. So let's test 4.7 against 4.64 divided by standard deviation over the square root of the sample size, which is quite small here, 10. This gives me a value of 1.58, which is a z-score of 1.589429, 0.9429. So if I start here and go back this way all the way to the beginning, I get 94.29%. So there has to be 44 in this guy, 44.29%. And I can do the same with the other one and just get the, take a 50% away, I'll get what's in here. So I'm testing 4.6 against 4.64, dividing by standard deviation over root n. This is going to give me a value of minus 1.05 and a z-score of 1.05 is 8531, 0.8531. Take away 50%, I'm going to get 3531. If I add 4429, I'm going to get 0.607960, 79.6% chance of being between these two values, 4.6 and 4.7. A company surveyed 400 people chosen from the population who bought the bar. 324 said they liked it. Population proportion 324 out of 400. Divides evenly, 0.81, which is p. 1 minus p has to be 0.19. We're asked to do a confidence interval to 2 decimal places. So I have 1.96 by the square root of p times 1 minus p, 0.81 times 0.19 over n, which in this case was 400, and 1.96 by this guy. I can round this to 2 decimals. It's going to give me 0.04. So that p in the middle of 0.81 is going to be between the values of, add 4 onto 81 to get 85 and take 4 away to get 77. So you can see here. On to part B, we're talking about these confidence intervals again for fixed n and p hat. So are these statements always true, sometimes true, or never true? Okay, well, let's have a look at a bit of information about this 1.96 times the square root of p times 1 minus p over n. You've probably seen before that this p times 1 minus p, which is near the end of this question, this is equal to a quadratic. P minus p squared, which is an inverted quadratic. It looks like this. And our values, the max value for p and the min value for p, starts at 0 and finishes at 1. So 1p can be 100%, 1 minus p would be 0, and you get back to the 0 again. So what we know from symmetry of quadratic curves, that the midpoint here is going to give me my max value, which is a half. So the max value of p will be a half. In this case, it'll give the max return of this 1.96 times p by 1 minus p over n. So that's what this question is based on. As we're climbing up the curve, n can change, p can change, what's happening as we go down the curve. And we know we have symmetry across here, so 0.25 and 0.75, if they're those 2 points, would give the same results. So let's have a look at the questions in relation to this. Now, I'll just differentiate this real quick. We're going to get 1 minus 2p if we differentiate that. If we let that equal 0, we get 2p is equal to 1. So this is the calculus near the end of the question. That we'll just do it now, seeing as we're here. So back across. When forming confidence intervals for a fixed n and p, an increased confidence level implies a wider interval. Well, we've seen this before too. A wider confidence level. Well, if I go 68%, one standard deviation approximately, this is the width of my, what are they calling it? A wider interval. Increased confidence level implies a wider interval. Here's 68%. Well, this is going to be always true. There's 2 standard deviations. It's going to be wider. That's approximately 95%. So this is definitely always true. The second one, as the value of p hat increases, we're just calling it p here, for fixed n, the estimated standard error of the proportion increases. Well, this is based on this guy. It is going to increase to a point, this point here, but then it's going to decrease back down. So this is sometimes true because it is going to increase as along here the value of p is increasing. This is p. It is going to get bigger and bigger up until halfway across, and then it's just going to get smaller again. So this is sometimes true. As the value of this increases, the estimated standard error increases. Well, that is true. As it increases, the standard error is always going to increase up to that midpoint again. And as n, the number of the sample, increases, the estimated standard error of the proportion increases. Well, this is not true here. As the sample increases, the standard error here is going to get smaller and smaller and smaller. And you could do a quick sum here. We could just do the square root part. The square root of 0.5 by 0.5, the max value on top there that we saw earlier, 0.25. If we take 100 as the sample, this will give 0.05 as this part of the standard error. We haven't multiplied by 1.96. If we take 1000 as the sample, we're going to get 0.0158, and 10,000 obviously getting smaller again, 0.005 if you check these on a calculator. So this is never true. So we're going to have, that's never true. Keeps on rubbing out, but you see what they are. Never true. This is sometimes, no, this was always true. Second one was sometimes true, and the first one was always true. We've used calculus otherwise to do this already. Just multiply it out and let it equal 0, and hence find the largest possible value of the radius. And this is an unusual way to state this again. So let's look at the max value of this. 1.96 by the square root. We've seen it's 0.25, and the sample size here is 800. And 1.96 by this guy is equal to 0.0346. 0.0346. So we have p here. It's spreading 0.0346 that way, and it's going 0.0346 that way. So if we imagine p is the center of a circle, the radius of this circle, if we draw it around, is going to be 0.0346. So that is the largest possible value of the 95% confidence interval, 3.46% if you want to write it as a percentage.